Thank you very much. It's a pleasure to be here. It's my first trip to Lisbon. Very nice. So this is joint work with Justin Sirignano from the University of Illinois Urbana-Champaign. And so this is a study of limit order book data at high frequency, where we use deep learning techniques to uncover some nice properties of this data. So it's not a talk about new innovations in deep learning architectures. We're going to use well-known things, but we're going to show that they're very efficient in uncovering information from this data. So I will focus, that's what I will focus on. And it's a paper which you can find online on SSRN with the same title. So if you're interested in more details, I refer you to the paper. Okay, so this study is about understanding price formation. So what is price formation? Well, this is the general name given to the mechanisms through which supply and demand and perhaps other factors in markets lead to the determination of the price. So it's well known that market prices react to supply and demand. But the question is how exactly? So suppose that you know the limit order book, which is the supply and demand curve instantaneously in some market, and suppose you know the entire history of the limit order book up to that point. Can you predict something interesting about the price move, the next price move? That's the simplest question that you could ask in terms of price formation. Intuitively, yes. Intuitively, all this information should help you do a good prediction, but it appears extremely difficult to get a quantitatively satisfactory answer to this. So ideally, what we would like to do, we have all this limit order book data, we have the order flow up to time t, and we have the price history and perhaps other things. And we would like to build a map which maps this to the next price, tell us where the next price will be. And that's what I call a price formation model. So this map, call it F here, can depend on only the instantaneous state of the limit order book. It can depend on the history of the limit order book. There are different ways to think about this, path dependent or not. And this map can be more or less complicated. It can be linear. It can be a time series model. It can be an agent-based model. So all the models of price formation can be thought of in this way in a very abstract sense. And then the forecasting frequency delta t can be different. You can be very ambitious and want to forecast much ahead, or you can just forecast one step ahead and so on. So all the models that you think of in market structure, high frequency, can be thought of in these terms. Okay, so the first question that I'm going to ask is this map universal or is it asset specific? What does it mean? Well, this map sends the price history, the order flow history of that particular stock, and to a prediction about the price at the next step. But is this map the same for IBM, Microsoft, Google, or some penny stocks, some large tick stocks, small tick stock, or is it different? Well, if it's not very clear, because if you look in the literature, like the market structure literature, doesn't build different models for different stocks. There is an abstract market structure model which is supposed to apply to everything. On the other hand, when practitioners build models for short-term prediction or trading or execution, they only use data from that particular stock. Nobody uses data history from stock A to build an execution or prediction model for stock B. They just don't do it. So it seems that while the theory assumes it's universal, people really don't believe that. On the other hand, there is a lot of empirical literature suggesting there are lots of universal relations that are the same across different stocks and markets and time periods. Okay, here I cite some studies related to scaling, but there are a lot of these studies pointing to a lot of universal features. So how universal is it? Can we really build a model that holds for all stocks? And then there is the question of stationarity. So suppose I have a very good performance on some sample. How far ahead can I take this model? Is it going to work tomorrow? Is it going to work next month? And so on. Again, there's this assumption of non-stationarity being the default assumption. They say, well, everybody says, you shouldn't use data more than a few months old if you do high frequency. If you do things like, if you build a risk model, people say, oh, you should never use data more than 3 or 4 years old, and so on. So it seems that the default assumption seems to be it's not stationary. So we're going to ask these two questions when we look at the data. So first question is, what is this function f? Does it even exist? And then is it stable across stocks and markets? And then is it stable across time? These are the three questions. And can we estimate this function? Can we get hold of this price formation mechanism? Okay, so in principle, we have lots of data to answer these questions with. We have petabytes of data on transactions, order flow, and order book dynamics. We have the entire tick-by-tick history of order book dynamics in listed markets. Question is, why haven't people been exploring this, to answer these questions? And if you look in the literature, in the econometric literature at least, people just don't look at this. They look at prices only. And I never understood why people only look at the price. Well, they have this data. I mean, they have all the supply and demand curves every millisecond, and they only look at the price. It's very strange. So the answer is it's really difficult. These are high-dimensional data sets, very complicated, and it's not easy to build parametric models, explicit models for them, stochastic models for them. So I think here's a field where the machine learning techniques can be of great help, because we simply do not have good statistical or stochastic models to deal with this. We have some very simple models, but they are not able to quantitatively deal with all the complexities of the data. So it seems very natural to use but the techniques that I'm going to explain to explore this data, you can think of as non-parametric techniques, which are capable of dealing with complex functional relations in a flexible way. Okay, so in this study, we're going to use a deep learning approach to explore the relation between order flow, order book histories, and price dynamics. And to use deep learning, we're going to use a very large data set. So we're going to use a large high frequency database of all electronic market transactions and quotes for US equities on the NASDAQ for 5 years. So we're going to have 5 years of tick-by-tick data for all stocks traded on the NASDAQ. All the order book events are included in this. And we train on this data set a deep neural network. I will explain to you the architecture and how it's done and so on. And what I will show you is that we uncover evidence, quite convincing evidence, for a stable, universal, and stationary price formation mechanism, meaning that the map which sends the order flow of a stock to the next price, we show that it's the same map across all stocks all the time. And this really surprised me. I had to check and recheck and pre-check this 10 times to convince myself that we're not doing something stupid. There's not a bug which tests it in sample and so on. So I'm going to show this in detail. And what we show is that this universal price formation model can be estimated with a deep neural network, and it exhibits stable out-of-sample accuracy across time, even 2 years out of sample, which, again, really was very surprising for me. And it even works for stocks which are not part of the training sample. So I'm going to show all these things one by one. Okay, so what is the data? So the data that is used for training is 3 years of tick-by-tick NASDAQ limit order book data for 1,000 stocks. So this data contains all the quotes and trades in the order book for all these stocks. So there's something like 100 billion order book events. So this is comparable to a lot of the applications in deep learning you see in other fields. You have lots of data. Otherwise, you can't really do these things. So we split this data set into two parts. We use the first 2 years for training, and then we use the last year and a half for testing, okay? And here there are lots of things that you could do. What I'm going to present here is the simplest thing that you could try to do here. We use the order book history up to a price change. So here we're going to focus on price changes, so the focus will be on price prediction. So this data set contains irregularly spaced events, all the order book events, the cancellations, new orders being sent, and so on. But we're going to focus on price changes. So the price changes are a subset of these. So let's call them tau 1, tau 2, so on. So we look at the order book history up to a price change, and we try to focus the direction of the next price move. Okay, so that's very, very simple thing to do. And it's simple, but it's easy to evaluate if you're right or wrong, because then you check, what happened, what did you forecast, am I right or wrong? So it's very easy to evaluate. Okay, so the type of snapshots that we have in data look like this. So for each tick in the data set, we have the full order book for each stock. Okay, so I think everybody knows here what that is. So we have the price and size. But you can think of the problem of forecasting the price direction as a classification problem. So you have the history of the order book up to time tau k, and then you want to say if at the next price move it's going to go up or down, and if it goes up, is it going to go up by one tick, more than one tick, or two ticks, or more than two ticks, and so on. And so here I can have 3 states plus or minus 1 and 0, or I can have 5 states or more. Okay, so you can think of this as a classification problem, and this is something where neural networks have been used a lot. You classify streams of data into different types. So here I can think of this as a 3-state or 5-state classification problem. So what do we use as input for the prediction? Well, the state of the order book, that's the very least, but I will also look at the case where we use the history of the order book. And one way is to input the entire history in a raw form. What we will do is we'll do it in two steps. We will learn features from the past history, and then we will have a network that forecasts based on these features, and I will explain how. Okay? And to compare this with another thing that will serve as a benchmark, we will compare it just in the first few slides with a linear model. So one model that has been used a lot in high-frequency data is the vector autoregressive model. You take the same variables and you build the linear vector autoregressive model where you will try to learn linear features of the data, meaning linear combinations, and then you forecast the price per direction from these linear features that's shown here on this slide. But you can think of it as a Cox model with linear autoregressive features. So what we do here in this study is what's shown below. It's a multi-layer or deep neural network. So what this does, instead of doing linear combinations of the inputs, it does a succession of iterations where at each iteration you intertwine 2 operations. The first operation is a linear combination with some weights that I denote theta I. So that's one layer of the neural network. And then in the second step, you apply to this linear combination, you apply some absolute value function or some smooth version of the absolute value function, which is shown here, this function phi that is called softmax function. Okay, so you intertwine these, so you do bilinear combination, softmax, linear combination, softmax, and so on. If you do it n times, that's what you call a n-layer neural network. Okay, so that's the story. Now, here, this architecture works if you do static classification. So if you, for example, if you do image or pattern recognition, you will map images to cats or dogs or whatever. That's static. But here we have time series. So When you have time series, there is an additional constraint that at time t, you cannot use the future to forecast your thing. Otherwise, you always get nice results. So this means that you have, at each point in time, you learn when you do the learning phase, you go through your data in the order of time, and at each point, you only use the past data to train. So for this, there have been designed special architectures called LSTM, or long short-term memory networks. So this is described in the last line. So at each step in time, we use a neural network to learn the features from the previous data, and then we use these features that are called HT, learned at time t, to forecast the price at time t. So this architecture is shown here. It's an architecture that was first designed by Hochreiter and Schmidhuber in '97. It's called a long short-term memory network. And I would say that this has been one of the most important innovations in neural network theory since the early 90s. So all the things that we're talking about now, deep neural networks, all the techniques and algorithms that are used in what you find in the literature now were actually in place at the end of the 80s. And I know, since I was a student in the early 90s and I read books where it contained all these things, the only thing that was not there was this. And because at that time everybody was doing static data recognition things, and the treatment of time series is really more complicated, because you need to have a structure that respects the causal constraint. And that was the idea of Hochreiter and Schmidhuber. So the idea is that observations are in the bottom, they're ordered in time, and at each point in time, you look at the past data, you learn from the data, you update what we call the historical features of the data that I call here H. So these are updated at each new observation. So this is done but through a neural network that only looks at the past data. And then the forecasting takes place only through the features. So that is a more efficient way of taking all the past history and then stacking it up to time t. That's not really something that you can manage if you have large time series. Anyway, okay, so we have this network structure. So in our case, at each point in time, we look at the current order book, the data plus the internal state, what we call internal state HT, which is a summary of the relevant features from all the past history of the order book up to time t minus 1. And training these networks is very costly in terms of computational time, because when you want to compute the loss function in the phase of supervised learning, you have to go back in time and compute the gradient with respect to all the points back in time. So it's quite a large calculation, and I would tell you how it's done. So how do we train these networks? So as I said, what we have is a large database. We split it in two, and we apply an approach known as supervised learning to train to select the weights in the network in sample with the training data set. So supervised learning just means you estimate the weights in the neural network using a large data sample where you minimize the in-sample loss function. In our case, what we use as loss function is the relative entropy of the forecasted distribution with respect to the empirical distribution. So it's a very straightforward approach that is very commonly used. The issue is that the number of parameters is huge. Okay, if you have 50 neurons per layer, and if they're fully connected, you have 50 squared parameters per layer, and then we have 3 layers per observation time. So even if you sample only at price changes, not all ticks, well, you have hundreds of thousands of parameters, if not more. So here, the approach that is used in this field is to use a stochastic gradient descent, because you're optimizing a loss function in dimension hundreds of thousands. It's not really a trivial optimization problem. And the gradient is a very large vector. It's so large that you can't even store it even once. So you, instead of storing the gradient and doing a straightforward gradient algorithm, you have to update parts of the gradient vector, which is huge, in some way that updates your training. So what we do is an asynchronous stochastic gradient descent. So it means we select a subset of the vector. We only update the gradient for those components, do an iteration and so on. And the gradient is computed by using backpropagation in time. It's basically the chain rule, but it's a very big chain rule applied along all the time points back in time. So it's just a huge gradient calculation and then a gradient, a stochastic gradient report. So again, in theory, it's straightforward. It's a computationally horrible task. And it's very expensive computationally. So here in this study, we use a cluster of 500 GPUs, each per GPU allowing to parallelize the computation across thousands of cores. So it's not something you want to do every day. So here is again how the asynchronous stochastic gradient descent works. And this is important because there's no way that you can have enough memory, even if you have a supercomputer, to hold the gradient in your memory if you compute it in a naive way. You cannot do that. Anyway, but again, all this is well known. This is not our contribution, super well known. So we just apply. This is the interesting part, is what do we find when we do it? So what we did is we trained such a neural network, LSTM neural network, first on individual stocks. So we try to forecast price moves from order book history of each stock, and we train it on the same stock. And then we have this strange idea. We say, well, let's train it on all stocks, or at least a large number of stocks. That's what I will call the universal model. In both cases, the architecture of the networks is the same. The objective function is the same algorithm is used, and so on. And then we're going to compare the jointly trained model, the universal model, with the single stock model. And we're going to see what happens. And so here is, so first, just as a sanity check, we compare the forecasting accuracy of the model with a linear model. A linear model is not stupid because it captures the trend. So if there's an upper trend, it captures it. So if you cannot beat a linear model, let me just stop doing this, close shop, and go back to doing ARMA or something like that. So, it's what we see is that it does beat a linear model. Okay, I mean we didn't spend my grant, doing all these calculations on supercomputer for nothing. So it does capture something a little bit more sophisticated than just a trend. So if you look at the increase in accuracy, so the accuracy is the fraction of outcomes that are correctly predicted out of sample. Well, you see that, you have a 5% increase on average. So each point on this histogram is one stock. And if you compare the two distributions of accuracies across stocks, you clearly see that the red distribution, that is for the deep neural network, clearly beats the linear model. But that's not really the emphasis, because this is not very hard. Anything can beat the linear model. Now, here is a more interesting graph. So here is a graph where we compare where we look at the increase in accuracy, so the accuracy of the universal model minus the accuracy of the stock-specific model on the same data. Okay. So this is, what does this mean? It means first we train a model on stock A, and then we train the network on all stocks, not normalizing by anything. I mean, where we're not taking the same sector, just throw them without any normalization and train it on the entire sample. And then we try to forecast the price moves of stock A with its own model and with this universal model. And what we see is that in the vast majority of cases, in this case, except for 4 or 5 stocks out of 1,000, out of 500, what we see is that the universal model outperforms the stock-specific model. Okay, so this is very interesting because one of the main arguments why deep learning is not used in finance is, well, there's not enough data. This stock is newly listed. I only have 1 year of data, so on. Well, here we're doing something really radical. We just pool together all the stocks, all the time series for all the stocks, and just train it on the whole thing. And it beats the stock-specific model. Now, why does it do so? So this graph shows you that it's a data size issue. The more data you have, the more you outperform. So here we look at the increase in accuracy versus the size of the training sample for each stock. And what we see is that for stocks where there is less data, the universal model, which is always trained on the whole sample, beats it by even larger margin. So this means that the advantages of having a larger data set and of pooling the data are overcome all the possible things you can think of, all the possible reasons you can think of for not pooling the data. Yeah, because they don't have the same tick, they don't have the same spread. And I really didn't want to do that. This is my co-author who wanted to do that. He's kind of crazy. I said, no, let's look at large tick versus small tick. Let's look at this and that. Let's normalize by the volatility and the spread. And we did all that. And it really did not improve. And you just do raw data, pool them without any normalization, and that's what you get. Maybe if you have a very intelligent way of normalizing, maybe you improve, but we didn't find that. Now, that was just, you have stocks that are in this sample, and you train it on lots of other stocks also, and it improves. And here is something even better. Here, so remember, we have 1,000 stocks. We train on 500 stocks, and then we test it on the 500 others, which were not used in the training sample. So here, I'm training it on, say, the first 500 stocks in the Russell 1000, whatever, and then I test it on the others, and the model has never seen data from those stocks. Now, surprisingly, it also beats the stock-specific models for those. Okay? So you compare two models. One has been trained on the stock you're trying to forecast, and the other one has been trained on other stocks which have nothing to do with this one. Well, they have nothing to do. They have something to do because they're exactly the same in terms of the pricing mechanism, but we think they are different stocks, but it still works. So what we see is that the out of the sample accuracy it's out of sample in two ways. It's a different period and it's different stocks, and the stock you're testing on is not part of the training sample. Well, it still works. And in fact, okay, this is a more complicated table. I don't know if you want to explain it. So here, we actually compare three things in this table. We compare a model trained jointly on all stocks in the first half, the first 500 or 464. Then we train another universal model on the second half. And then we test it against a stock-specific model, and the stock is included in the first half. Okay? So what we show here is that it's not relevant if the stock you're trying to test on is part or not of the training sample. It doesn't matter, because you're learning the same thing from all stocks. The only thing that matters is the size of your sample. That's it. Now, why does this work? Well, if you're really convinced by this market structure theory that there's a universal model which describes all markets, price formation is always the same in all markets, then say, well, sure, of course, I was saying this all the time, That's what I thought anyway. Okay, fine, but I think it just is the fact that, first of all, if you think about what we're looking at how order flow affects the price. Well, how does order flow affect the price? Well, there's algos which are trading on it, market makers and so on, you guys. And, you use the same algos for all these stocks. You're not using one algo for stock A, one algo for stock B, it's the same. So these algos will react the same way to the same stream of orders, same history of the order book. So not surprising that you find the same thing. But why does it outperform? It's because when you pull together the data for 500 stocks, it's for 2 years. It's like you have 1,000 years of data for one stock. Well, then you're going to learn much more, and you're going to see more diverse set of scenarios. For example, for one stock, in sample, you might have a flash crash. For the other stock, you might not have any flash crash. When you go out of sample, Well, if you train it on the big data set, then it understands what are the type of patterns which lead to a flash crash. So it can, try to predict that. Whereas if you only train it on itself, on the stock itself, it has never seen that, so it's not going to predict it. So it's really very simple to understand why it works. So what we show here quantitatively is that the diversity of the scenario set, the richness of the scenario set, which you obtain by pooling the data, outweighs any disadvantage you can think of, such as, it's heterogeneous, large ticks, small ticks, sectors, and so on and so on. And it really goes against the way we train models. I mean, most people here would just, if they have to trade 1,000 stocks, they would train 1,000 models or estimate 1,000 models and maintain them. Think of the effort which would go into to maintain 1,000 models for 1,000 stocks, as opposed to maintaining a bigger model. Of course, the number of parameters is huge, the effort in training is huge, but then one model. So it's really interesting. Also, for the purpose of newly listed stocks, things where you have no data or missing data. So there are a lot of implications for this finding, I think. Okay. Now, the next point is stationarity across time. So this is really something that people strongly believe in. They think that financial data are not stationary. And when we started the study, we talked to people in different banks and so on. They said, don't use more than 2 weeks, don't use more than 1 month. It doesn't, it changes anyway. The market changes, everything changes, and so on. Well, so here the test is, we train it on a training sample, and then we test it out of sample. And if you believe this stuff, then as the testing period moves away from the training period, the performance should deteriorate, because what you learned in December may be relevant for January, but maybe it's not relevant anymore for March, and maybe it's even worse for September. Well, we don't see any evidence of this. And maybe the sample is too short because it's only 4 years, but come on, this is high frequency stuff. So I don't know. I mean, I have only the data I have, but we don't see any evidence that the accuracy deteriorates as you go away from the end of the training sample. So here's, for example, the accuracy on the left for June to August 2015. And then on the right, the red curve is the same graph out of sample accuracy for January to March 2017. And the training period is always the same. It's the same neural network. It was trained up to May 2015. So if you do right after the training or 2 years out, I don't see any difference, and we did not find any difference, because what we're modeling is really the relation between order flow and the price. And I mean, again, if you believe the economics models, it's an immutable relation, which Walras was supposed to pinpoint in his book. It should not change ever, right? Well, I'm not claiming that, but I'm saying that we don't see any evidence that you should use a recent data sample. And in fact, in the paper, you will find more complicated tests where we shuffle the data, we train on something, and then we use. I mean, we look at all kinds of things to just check that. Because if there's a trend, you might say, you're just catching the trend and so on. But, I mean, 2 years, 1 month, one day, but this doesn't make any difference. So this, I think, has also some implications, because the practice I see in markets is estimate models using recent data, because everything is non-stationary, supposedly. And when it comes to intraday modeling, they use really short time windows, because somehow even last week is not relevant, or maybe 1 month is relevant at most, and so on. But we don't find any evidence of this. And I was really, again, surprised. But, it is what it is. And here on this graph, for example, we change the duration that separates the training set from the testing period. And what we see is, there is no evidence that if you if you go farther from the training set, you deteriorate. On the contrary, what we see here is that if you increase the length of the training period, you improve performance, even if you go far in the past, up to 2 years. That's the largest that we can go. So this goes against the advice that only use the recent data because it's non-stationary. Here, if we use 6 months of data, we increase accuracy and so on. And finally, the last thing I'm going to show is path dependence. Okay, so here, the simplest thing you could do, well, first of all, you have to make a choice. How many lags do you keep for the order book? So here, one lag is not one tick, but it's one price change. So on average, for all these stocks, it's around a second or more than a second. So should we take only the last, state of the order book, or the last 10, or the last 100, and so on? So actually, and what we do, so this is done by changing the number of time units in the LSTM network. So here is a comparison of the LSTM network, which takes in lags, with a feed-forward neural network, which takes only the current state of the order book. So in the literature, if you look at analytical models of order book, including the stuff that I was doing before, they're Markovian, because that's the only thing we can calculate with. Well, except for the people who do the rough models, they do very complicated things. But for simple people like me, we have been doing Markovian models. And here, the Markovian case would be a feed-forward neural network, which uses only the current state of the order book. And if we compare the LSTM network that we use here with the Markovian case, well, you can see that really it pays to look at the history. And that's not very surprising, because people follow, they do all these trends and so on. That's because they think it's relevant. So that's, again, not surprising. But what we see in this graph is that if you go back 5,000 lags, which on average, these are price changes, so it's roughly 2 hours for an average stock in the sample. Well, you learn more, you have more information for forecasting just the next price tick than if you go back 100 lags, for example. So this means that there's all this literature about long memory, long rate dependence in the order flow and so on. Well, in practice, what this means is that you really have to use history-dependent models if you want to do forecasting, because you gain here 1% in accuracy, which is not small, if you go back to 2 hours on average, which is very long for forecasting one tick. You say, why is it relevant to go back 2 hours? Well, a lot of things happen intraday, and in 2 hours you can capture information that you cannot see from the last 2 minutes. So there is path dependence, I'm sorry, so we have to live with that. And this is interesting. I think this graph is a big argument for using such models, because there are not many analytical models available where you can even write down a tractable path dependence of the price versus the order flow. It's really difficult. And even if you do that, then it's very hard to do anything with it. Here, the model is flexible enough to capture, history dependence. So, that's I think this is a very strong argument for using these models. They're non-explicit, but you can do things which are quite hard to do with explicit analytical models. So this is the conclusion slide. So I think I've tried to present evidence that there is such a thing as a universal price formation mechanism underlying intraday data, and we can estimate it through a deep learning approach. The universality shows up by looking at stability of the performance across time and stocks and sectors. It seems insensitive to sectors, large tick, small tick pictures, and so on. And interestingly, the universal model it's not just equal in performance to stock-specific model, it beats them even for stocks not in the training sample, because it uses much more data and a much more diverse set of scenarios. That's it.